Hello everyone. Please type yes in the chat if you can hear me well. Okay, perfect. We will start in 5 minutes just to give more time for people to join, and then we will start our session, inshallah.
Hello, the person you are calling is on another call at the moment.
Okay, it's time to start. Hello everyone. This is Adel. Um, I would like to welcome you to the OPA 6 internship guidance session for the reservoir discipline titled PVT, presented by instructor engineer Ahmed Khalid. Engineer Ahmed is a reservoir engineer with working experience in heavy oil, light oil, and gas reservoirs under various development strategies like steam injection and water flooding, and with different lithologies like carbonate and sandstone reservoirs. In two operators, having experience in reservoir simulation, reservoir management, classical reservoir engineering methods, reverse booking, equation of state, pressure transient analysis. Such a great profile, Engineer Ahmed, and it's a pleasure to have you with us today. You can now start your presentation.
Thank you. I'm going to share my presentation now. So can you see the presentation?
Yes, I can see it, but the voice is not clear. It's like there is something like air or something that's interrupting your voice.
Can you hear me now better?
Yes.
Sure. Good evening, everybody. I'm Ahmed Khaled, a reservoir engineer with over 6 years of experience in two major operators. And I'm going to talk tonight about the PVT. We are going to talk about what is the PVT, the importance of the PVT in reservoir engineering, what are the 5 major reservoir fluids, also what are the fluid properties that we count on in the analysis of the PVT, what are the sampling methods to obtain the PVT, and what are the experiments of the PVT that we are performing in the lab.
Excuse me, Engineer Ahmed. There are some people that's complaining from the voice, saying it's not clear. Can you please try to switch to another mic or something?
I'm going to try another mic.
Okay, yes, please.
Can you hear me now?
Yes, it's much better now.
Okay. So I'm going to share my screen again. So we are going to discuss today what is the importance of the PVT, what are the major classification of reservoir fluids, what are the fluid properties that we are interested in for the reservoir fluids, what are the sampling methods in order to get a sample to be analyzed to get the PVT, and what are the experiments that we are going to perform on the PVT samples. So, in generally, in petroleum engineering, PVT stands for the pressure, volume, and temperature analysis. It refers to the study of how the reservoir fluids, oil, gas, and water behave under the different pressure and temperature conditions, which is very important for reservoir engineering, reservoir production, and simulation, because we are producing fluids from the reservoirs under different pressure regimes, and there are pressure drops throughout the reservoir into the completion, into the wellbore, and into the surface. With this pressure and temperature drops, the properties of the oil and gas, I'm sorry, but there are someone
is knocking on the wall in the next apartment. I'm sorry for this, but I cannot. I will try to clear my voice. There are pressure and temperature drops throughout the reservoir till we reach to the surface. With this pressure and temperature drop, the composition or the properties of the fluids, oil and gas, differs under the different pressure and temperature conditions. For example, if we have pressure, so we are going from the reservoir which has a high pressure, and then we have a pressure drop throughout the perforation till we reach to the wellbore and reaching to the surface. And with this pressure drop and the temperature drop, of course, we will see the effect of the gas releasing from the oil and becoming free from the oil composition. Also, the relative volume of the oil and the gas and water will change because the fluids will expand or contract under the change of the pressure and the temperature. What is the importance of the PVT? It determines these fluid properties such as the density, the viscosity, and the compressibility under different conditions in terms of how the density and the viscosity and the compressibility of the oil and gas will change when we have a pressure drop or depletion of the reservoir. Also, it defines the phase behavior of oil, of gas, of condensate. And we will see the difference between the three parameters in the next slides, which will be very important in some studies because, for example, in condensate, it's very important to understand the behavior of the fluid. And we are going to talk about this issue in details as it will require a special study, especially for the condensate, and we'll see in the next slides why. It's important to understand the behavior of the condensate in the reservoir because it's affect very well the productivity of the reservoir and how we can produce a reservoir and the development plan of this condensate reservoir. Also, it's an input for reservoir simulation model, and we can have it in the simulation model either through correlations or either through tables or either through an equation of state. The equation of a state is like the gas equation of a state, which is PV equals Z and RT. And it's very important in the type of fluids that have very radical change of the composition with the pressure and temperature drop. And we are going to see this in the 5 reservoir fluid section. Also, it's very important to understand the recoverable reserves and protection strategy. Because if you remember the oil in place equation, which is the volumetric equation, it's function of the beta O, which is the oil formation volume factor. And we are going to explain this terminology later. But the volume of the oil in the reservoir is different when it comes to the surface. And this difference is related to one of the PVT properties, which is the beta O, or the oil formation volume factor. Also, it's important to design the surface facilities like separator, pipelines, and compressors because it gives us some information, important information about the amount of gas dissolved into the oil, the characteristics of the oil itself, if we have a flow assurance issue like asphaltene, like wax, like hydrate formation in gas reservoirs. Also, it's very important to understand how to size the separator based on the gas oil ratio, based on the composition of the gas itself. So generally, the type of hydrocarbons or reservoir hydrocarbons are different, and we will have in the next slides how to differentiate between them. But the major difference is the amount of the gas associated to the oil, or if the oil itself is, or if the hydrocarbon itself is mainly in the gas phase. So most of the books classify them away from the dead oil or the dead oil, which is away from this 5 reservoir phase, the dead oil is an oil with a very low gas dissolvent. Any oil or any hydrocarbon has some gas dissolved in it. And if we reach to a certain pressure and a certain temperature, we will see the gas will get out free from this oil composition. And it's called bubble point pressure. And we are going to talk about this issue in detail. So any oil composed of some light components that at a kind of pressure drop start to come out of the solution of the oil and become free. So the light components leave the oil, keeping the heavy component, and it's a gradual process. So in the dead oil, which is not in here, we have a very low gas. It's considered non-gas associated in this oil. Here we have 5 reservoir fluids. The first one is the black oil. There are some definitions that we need to understand in these diagrams. So this is called a phase diagram. The phase diagram is a pressure and temperature relationship. And we have here lines. This line, which is huge line, the area in between represents the 2 phases, meaning that at this pressure and temperature inside these lines, we have 2 phases, oil and gas together. Above it, we have only single phase. We have a point that is called critical point. This critical point represents the point above it. We cannot have 2 phases together. They are not together. Only one phase can exist. So above this line, we have only single phase. So what is the characteristics of the black oil reservoir? If you checked in here, like I mentioned, we have here, this is the initial reservoir pressure condition. And this is the temperature of the reservoir, which will not change. If we are going to produce this reservoir, the pressure will drop till we reach to this value. Reaching to this value, we will start to see the first bubble of gas that we can see, and it's called bubble point pressure. So at the black oil, we can see that there are lines in here. Here in this line, 100% of liquid and 0% gas. Here, 90% liquid and 10% gas, and so on. So in the black oil, we can see that with the constant pressure, almost constant pressure depletion, we can see the same amount of drop of gas will happen. The droplet or the amount of gas will come, it's almost equal, meaning that there are even spaces between the lines. Also, from the characteristics of the black oil phase diagram, is the critical point is to the right from reservoir. We can identify the black oil with field identification, like we are going to talk about it later. But if you have a composition of any fluid, you can construct this phase diagram, and you can see what is the type, almost the type of the fluid that you are having. This can be constructed by any software or PVT software, like for example PVTB, PVT SIM, or fluid modeler of Schlumberger, or PVTI double. So in the black oil, we start with pressure above the bubble point pressure. Once we reach to the bubble point line, first bubble of gas appears, and then with the continuous drop, there are additional gas that comes out of the solution, but it's kind of equal spacing. With additional drop, we have this almost similar amount. This point represents the separator conditions, meaning that if we the pressure, any fluid that we produce, we start from reservoir, going to perforation, then going to the completion tubing, up to the surface, and then after the surface, we go to the facilities, which is consistent of separators and then tank. So at the separator conditions, separator pressure and separator temperature, which will be, of course, lower than the reservoir pressure and temperature, we also have the two phases at this issue. Another type of the oil, it's called the volatile oil. In a few words, it's more gaseous oil. It has a lot or a higher amount of gas oil ratio compared to the black oil. And it can be characterized by the critical point going a little bit near to the reservoir pressure. Also, the distance between lines are not equal, meaning that if we started production from here and we have the first bubble of gas in here, then with small pressure drop, we will have a higher gas. And if we come to a certain limit, it will be a lot of gases coming. So the gas oil ratio of the volatile oil is generally higher than the black oil. And from the phase behavioral diagram, you can see the space between the lines are not equal. For the gases, we have three different type of gases. Let's start with the most important one and the most one that we have troubles into the producing, which is the retrograde gas condensate. As you can see, we have in here the critical point for the first time is to the left of the reservoir pressure and the temperature. And if you can see in here in this area, we cross the dew point line. In this case, it's gas. So we have a dew point, not a bubble point. The dew point is a point, the first point we see the first droplet of oil or droplet of condensate. So gas has some heavier components. With the pressure depletion, we see some oil droplets in it. So once we cut the dew point line, we start to have some liquid droplet, and it's continue until we reach to this line, which we cut the same line twice. So in this area, we have a liquid droplet, then the liquid come again into solution. The main issue of this retrograde gas is that around the wellbore or around the perforation, we may have a phenomena is called condensate banking or condensate blockage that may affect the productivity of the gas. So in the gas condensate reservoirs, it's very important for us to keep the bottom hole flowing pressure above the dew point pressure in order not to damage the reservoir through the condensate banking that will have dropping if we dropped below the dew point pressure, and also to keep this liquid into solution of the gas, because it's very important to produce this condensate. It is very has a very good characteristics and is very expensive compared to the gases. Some companies they develop a strategy that's called gas recycling. They produce the condensate gas, separate the condensate at the surface, and re-inject the gas again, the dry gas in the reservoir, in order to keep the reservoir pressure above the dew point pressure to avoid any gas banking. The other two types that we are having are wet gas and the dry gas. The main difference between them is the separator conditions. If you can see, the wet gas, it stays gas at the reservoir conditions. But as separator conditions, it has a little bit, some droplets from the condensate as a surface. However, in the dry gas, it's a kind of theoretical, but it has very, very low amount of liquids that can be dropped. And we are going to see the comparison in the field identification methods. So in general, we have classification of the main 5 reservoir fluids or 5 hydrocarbon fluids that we can see: 2 oil, black oil, and volatile oil. The main difference is the amount of gas. Retrograde gas, which has a retrograde effect, like we illustrated, and wet gas and dry gas, and the main difference between them is the separator conditions. Anyone have any question? No questions? Okay. Sure. So I don't have a PVT sample or a composition to draw the phase behavior, and I know I need to know from the field parameters what is the reservoir fluid that I am having. So we have some identification from box. It can differ a little bit, but it's general guidelines that can help you to identify what is the fluid that you are having. So for example, in terms of producing gas liquid ratio, if you have a gas liquid ratio below or gas oil ratio below 1750, it's a black oil. But in some books, it can be lower than 2000. For volatile oil, it's kind of from 1750 to 3200. For retrograde gas, it's more than 3,200. For wet gas, it's more than 15,000. For the dry gas, it's 100,000 or more. Also the API, and here what I mean it will be clear. So for black oil, generally below than 45. For volatile oil, it should be higher than 40, and so on for the retrograde gas. So it's common criteria for them. So here we can depend on kind of the gas oil ratio. If we have a gas oil ratio above 10,000, 15,000, we can have it with gas. From 3, 4,000 up to 10, 15,000 is retrograde gas. If we have a very, very high gas oil ratio, more than 100,000, so it can be classified as a dry gas. Kind of also the color can have us dark colored, lightly colored, and water white. And this is, of course, related to the API itself. This classification is just for the engineering purposes to understand quickly what is the type of fluid that we are dealing with in order to prepare facilities for production or so on. But if you want to identify clearly the type of the reservoir fluid, we need to take a PVT sample and going to for analysis in order to know the fluid and perform a full field development plan according to the PVT in addition to the other geological and reservoir engineering aspects. Also, of course, if we have a change in the phase behavior, like I mentioned, the black oil and the volatile oil, we have a bubble point, which is the point or the pressure that the first bubble of gas appears. In terms of retrograde gas, we have a dew point. In terms of wet gas and dry gas, we will not see a pressure drop across the reservoir or even at the completion. We will see it at separator conditions in case of the wet gas. Also, the C7 plus kind of indication. If we have a more than 20%, most likely it's black oil. If we have a 12.5% to 20, it's volatile oil. And if we have a less than 12%, it's retrograde. Less than 4 is wet gas. On less than 0.8, it's also dry gas. Also, the oil formation value factor, if we have a kind of above 2, it's a volatile oil, and the black oil should be kind of below 2. Despite the fact we have seen black oils with around 2.5 or so, but like I mentioned, it's just kind of for engineering purposes guidelines, can be changed a little bit. It's not likely, and the most accurate way to get it is to perform a complete PVT analysis. Also, from the production trends, we can understand the type of the reservoir that you are having, like I mentioned to you. So in case of the gas oil ratio, we will start with constant gas oil ratio till we reach to the bubble point pressure, then it will increase and then start to decrease a little bit because of the mobility of the gas compared to the oil. In case of the volatile oil, it will be the same, except the fact that the gas oil ratio will be a little bit higher. If we have a retrograde gas, it will be constant and then it will increase. and in case of the wet gas, it will remain constant. Here, the retrograde gas will increase because of the condensate banking that I talked about. The condensate will drop into the reservoir with the production. Similarly, the ABI trends will follow the gas oil ratio amount. So if you can see, the ABI will drop because of the gas coming out of solution, keeping the heavy components only. And after the gas oil ratio drops because of the mobility, the ABI will increase. Similarly with the retrograde gas. However, the wet gas will remain constant because we don't have a phase change in the reservoir in the case of the wet gas, since the liquid will drop at separator conditions only. In terms of fluid type occurrence, we tend to have heavy oil at shallow depths, for example, 2,000 to 3,000, 5,000 feet, some cases. Reaching to more deeper reservoirs like 10,000, 15,000, we can have gas and oil. And if we reach to 15,000, 17,000, we will have a gas condensate or dry gas reservoirs. Also, from the density, gravity, and the capillary pressure, we tend to have gas above oil and the oil above the water. And if we take a pressure trend of the gas, oil, and water, so we'll have a gas pressure gradient of 0.04 to 0.1, depends on the density of the gas itself, and the oil from 0.23 to 0.33 depends also on the density of the oil, and the water from 0.43 to 0.5 depending on the density and salinity of the water. So if we have an RFT or pressure measurements in the same reservoir, we can draw the trend lines, identify the gas oil contact and the oil water contact. Any questions regarding the slides before I move to other slides?
We have the questions in the chat.
We have two questions, yes. Instead of gas recycling, how to deal with condensate RE to maintain pressure? Yes, the only way to prevent the condensate banking is to maintain the pressure above the dew point pressure. You either inject gas, if you can inject water, it will help. But if you not prefer to perform this in the gas condensate reservoirs, because if we have a water breakthrough, we will not produce any gas. So the most important thing is, like I mentioned, to try to maintain the bottom hole fluid pressure or the reservoir pressure around the wellbore above the dew point pressure. This is practically done by re-injecting gas at the crest. Also, how we can detect the bubble point where the liquid and gas has same properties. I mean the pressure equal bubble point pressure. It's like I mentioned, there are the composition of the fluid as a reservoir is single phase at the beginning. If you have a pressure drop and you reach it to this bubble point pressure, which differs from fluid to another fluid, you will see the first bubble of gas. How you can identify it? You will identify it using a PVT sample in the lab, and we are going to discuss this. So through the PVT report, you know exactly the pressure at which the gas will be separated from the oil at the reservoir temperature. Any other questions? Okay, so I will continue. So we need to define some parameters related to the oil or the PVT parameter that we are using. For example, we have the specific gravity of the oil, which is the density of the oil divided by the density of the water, and should be at the same temperature. Also the API, which is a standard that we measure the quality of the crude oil that we are producing, or the condensate, which can be calculated through this equation. If we put it as if with a we are talking about water, so the API of the water is 10. So also the higher the API, the more expensive is the crude oil that we are producing, and the more valuable, of course. Of course, the oil is sold based on specific parameters or specific blends, like for example, Brent, Texas West, or so. It has a specific parameters in terms of API and the composition. And based on these two parameters, the oil crude or the crude oil can be evaluated or can be assessed with the price. Another important parameter from the PVT is called the oil formation volume factor, which is the volume of the reservoir fluid at the reservoir conditions divided by or required to produce one standard volume of stock tank barrel. So the volume of reservoir oil at the reservoir condition divided by the same amount at the standard conditions. And the unit is reservoir barrel by stock tank barrel. And we use the sample of beta O, sorry, it's the symbol of beta O to represent the oil formation volume factor. So if we checked, this is the typical trend of the oil formation volume factor with the pressure and this is the beta O. Of course, it's calculated as a reservoir temperature. And of course, it differs from one fluid to another. So this is an example for one fluid. So if you check this like slope going up in here to reach the bubble point and then going down again. So above the bubble point, it has this slope, and with the increase of the pressure, the slope tends to go down because of the compressibility of the fluid. But below the bubble point pressure in here, it turns to the another direction, going to slope down. And this is because the gas coming out of the solution. One may ask a question: if you are comparing the reservoir volume to the standard condition volumes, so it should be at the pressure of standard condition, which is the 14.7 and 60 degree Fahrenheit, should be 1. But actually, it's not 1. The reason behind this, because it's at the reservoir temperature. It's not at standard condition temperature. So it will not be 1. It will be near to the 1, but not 1, because we are calculating the reservoir volume compared to the standard condition volume, but at the reservoir temperature, not at the standard condition temperature. Also, another parameter is the solution gas oil ratio, which is called RS. It represents the volume of the gas which comes out of the oil as the gas is moves from the reservoir pressure and temperature to the standard temperature and pressure. And it's very important parameter to identify the type of fluid itself. The unit of it is standard cubic feet per stock tank barrel, representing how much gas is totally dissolved and comes out of solution while producing this gas from reservoir pressure and temperature and going up to the standard pressure and temperature. And this is the typical RS shape. Above the bubble point is constant because all of the gas is it's dissolved. But at the below the bubble point, some of the gas come free. So the oil has only a few amount of gas. And this amount of gas is decreasing with the more depletion. So it measures the current amount of gas that's in the oil at the pressure and temperature conditions. If we checked, this is for example, if we have an oil here and we have a reservoir pressure above the bubble point pressure, so we'll have oil in here that going to separator and stock tank. And in this condition, we reach it to the bubble point pressure in here. So we have some gas out of solution will come here. But at separator conditions, we will see we still didn't reach to the standard conditions. So when we move to the stock tank condition, we will have another gas will separate it. So the summation of both of them is the RS. the summation of the gas that's separated through the separator conditions and the stock tank conditions. Because separator conditions is normally not at the stock tank condition. It's at a little bit higher pressure and temperature, 100 psi, 200 psi, according to the design. But the stock tank condition is 14.7 and 60 degree Fahrenheit. So we should sum the total amount of gases coming out from the separator conditions and from the stock tank. But what about if we are below the bubble point? So we'll have initial gas that will come out from the reservoir. So we should add it also. So in the terms of the RS, we only will have the oil that's coming out from, sorry, the gas is coming out from the oil. However, the produced gas will come out and will not be taken into consideration in the calculation of the RS, because the RS is at these conditions, what is the amount of the gas dissolved into the oil. If it's below the bubble point, it should be lower than the RS above the bubble point, like we illustrated in this figure. Oil compressibility represents the change of the volume of the oil respect to the pressure change. And this is in case of the above the bubble point. In case of the below the bubble point, we should take into consideration the free gas that we are having. So the compressibility of the oil will be also associated with the gas that will come out of solution with the pressure drop below the bubble point. So the shape of the oil compressibility will be like this. And this is the bubble point pressure. This is the type. The bubble point pressure will be here. Also, the oil density, which is measure the oil density, it changes with the pressure variation. And at the bubble point, we have the lower oil density. So in water flooding, generally, we prefer to start the water flooding at nearby the bubble point, because we will see in the next slide it has the lower oil density and the lower oil viscosity, and that will enhance the mobility ratio of the water flooding process. Oil viscosity is the resistance to the flow exerted by one fluid. For example, if we have a large viscosity, we'll have low flow rates. So heavy oil generally have very large values, meaning that it has low flow rates. So we need to reduce the viscosity in order to produce this oil. I've worked in the company which we have a very heavy oil reaches to 11 and 12, 14, and the viscosity reaches to 4,000 and 6,000 centistock at the reservoir conditions. At the surface conditions. So we are producing through steam injection and cyclic steam stimulation. We inject steam, heat to lighting or reduce the oil viscosity in order to be able to move better, enhances the oil viscosity, enhance the mobility of the oil relative to the water, and enhance the productivity of the oil. We can see that it's similar trend compared to the density, very similar. So we can see that, or we can say that oil viscosity and density are going hand to hand. Like I mentioned, the lowest viscosity value is nearby the bubble point pressure or the bubble point pressure. So it's preferred to start water flooding near to the bubble point pressure in order to have a better mobility ratio between the water that we are injecting and the oil that we are going to produce. Any questions? Any questions? Okay. Why the viscosity increase? Okay. Here, the viscosity increase is related to the pressure, we apply more pressure onto the reservoir and the fluid itself. So if you can check the other direction in here, it's decreasing or it's increasing significantly because gas comes out of solution, keeping the heavy components only. However, here it's related to more pressurizing the fluid itself. So the fluid is more pressurized, more compacted into with this high reservoir pressure. So it's increased a little bit, but you can see the change is not that significant. It's almost from 0.3 to almost 0.4. It's a very small change. And this is related to the compressibility of the liquid itself. The liquid is more compressible under increasing the pressure. Below the bubble point, like I mentioned to you, because of the gas comes out of the solution, keeping the heavy components only. So the heavier components will have a higher viscosity. Okay, I'm going to continue. For the gas PVT, it's important to have some parameters, but we will need to identify the gas equation of a state, like I mentioned, which is PV and RT. N is number of moles, P is pressure, R is the gas constant universe, temperature, and volume. And the ideal gas equations have some assumptions that the volume occupied by the molecules is not large compared to the volume of gas, and there are not attractive or repulsive forces, and all collisions are perfectly elastic. This is the conditions, meaning that there is no change related to the volume of the molecules itself compared to this. Also, there is no attractive and repulsive forces between the molecules itself, and there are no collisions between them. Of course, this is not the reality, so we have a modification or the real gas equation of state, which is BV, Z, and RT. And this is the correlation. V real is called Z V ideal. And the Z is called the compressibility factors, also called the gas deviation factor. And this can be calculated through this chart. For example, this chart can be used to calculate Z, or there are correlations like Abul Qasim and Schnock and other correlations. It's a function of functions called pseudo-reduced pressure, and the lines is pseudo-reduced temperature, and we enter, this can be calculated through other equations. It's not, we don't have time to take into consideration, but it's very easy equations. You get this reduced pressure and reduced temperature, enter the chart or the correlation and get the deviation factor or the compressibility factors. After you have the compressibility factors, you can calculate, not using correlation, a lot of functions. For example, the gas density, which is function of the pressure of the molecule, and the Z, the R, which is constant, depends on the units, and the temperature. And then you can calculate the density versus pressure. And the density versus pressure is an increasing trend in case of we have a gas reservoir. Also, the beta G, or the gas formation volume factor, is function of the pressure at standard condition, temperature at standard condition where they are constant, the Z that can be calculated from the function that I mentioned, the temperature and the pressure. If you have it, you can calculate the beta G. And the units is reservoir barrel per standard cubic feet, or it can be cubic feet per standard cubic feet. So this is the beta G. This constant can be changing based on the unit we are going to calculate. So if we are using this unit, the constant will be different if we used another unit. Also, the gas formation volume factor is the same definition of the oil formation volume factor, which is the volume of the gas at reservoir conditions to produce one standard volume of the gas at the surface. Similarly, the gas viscosity is the resistance of the flow exerted by a fluid. So the larger values will have a lower rate. Of course, if we have a high gas viscosity, it will be lower. But of course, the gas viscosity will not be that much. It's like components, so it's ranging from 0 to 0.5. Also, we have units of its centipoise or centistoke, and we can calculate the centipoise by multiplying the centistoke by the density. And we can transfer from this unit to this unit. But generally, in the reports, we have it in centipoise. By the way, the gas viscosity, we cannot measure it at the lab. It's calculated using correlations. However, the oil viscosity is measured in the lab. So if we have a black oil study or an oil PVT, we need to get the bubble point pressure, the formation volume factor, solution gas oil ratio, the oil density, the thermal compressibility, and the oil viscosity. All of them as a function of the pressure, as the pressure decreases from the initial reservoir pressure throughout the bubble point pressure to very low pressure. This is the general that we need if we are performing a black oil study for a PVT sample. For gas PVT sample, we need to have the Z factor, the gas formation volume factor, which is calculated from the Z factor, the specific gravity, and the viscosity. What about the black oil PVT properties? How we can get it? We can get it from reservoir fluid study if we have a sample, and we are going to talk about this later, or from PVT correlations. There are some correlations that match specific fluids in specific areas. For example, equations that we are using here in Egypt in the Western deserts, or correlation that we know that is matching our properties in the Western desert, so we can use it instead of taking a PVT sample. So the field data required in order to get the correlation, we need to get an accurate value of bubble point pressure. So if we don't have it, we will use another correlation for the bubble point pressure. So if we use a correlation for the bubble point pressure, and most likely we will not know exactly the bubble point pressure, we need the RS at the bubble point pressure, meaning the gas in solution or gas oil ratio at the early production stages. Also, we need the API of the stock tank, and we will need the specific gravity of the separator gas, and we can get it from the gas cells data. Also, we need the reservoir temperature, and we can get it from the well logs or other sources. We can get it easily from the RFT data. So if we want to calculate the oil properties from correlations, we need to have the RS at the bubble point, which is the gas oil ratio at the early stage of production, the API of the stock tank oil, and the specific gravity of separator gas, in addition to the reservoir temperature. So if you are going to have a fluid sample, there are different sampling methods: bottle hole sampling and surface recombination sampling. Before I go to this topic, if anybody has any questions. Can you hear me at least?
Yes, Engineer Ahmed, we hear you.
Okay. No questions? Okay, we are going to
We
move
have a question.
to the other topics. So sampling methods, which is the way that we can get a PVT sample to send it to the lab in order to have a complete PVT analysis that will help us into the reservoir studies if we have simulation, if we have field development, if we need to know more properties about our fluid. So the bottom hole is trapping of the volume fluid at reservoir conditions in the pressure vessel that will run into the wellbore while the wellbore is open hole. We didn't case it yet. And it's run through RFT log. So the RFT log has a probe that go into the formation, suck a little bit of oil, and keep it in the vessel under the reservoir conditions in terms of pressure, in terms of temperature. After that, it will be kept at the pressure and temperature condition, sent to the lab for analysis, and the lab will validate the sample if it's take it correctly, if we have leakage, if we have a pressure drop, if we have a contamination from the mud, and then after that. So the bottom hole sampling is taken using wire line or a DST at the reservoir conditions and kept at the reservoir conditions till reaching to the lab. When we can use the bottom hole sampling, if the flowing bottom hole pressure, we know that it's higher than the fluid saturation pressure. And it's very important. The fluid saturation pressure, which is bubble point pressure or the dew point pressure, depending on we have oil or gas. And it's very important to keep the bottom hole pressure above it. Why? If we have the bottom hole pressure below it, we will have some gas that will escape, that will come free and will not enter. So we'll have a misleading data related to the gas oil ratio. So the bottom hole pressure and the reservoir pressure at the time of bottom hole sampling should be higher than either the bubble point pressure in case of oil or the dew point pressure in case of gas. Also, the nature of the fluid itself should be able to be retrieved. For example, if we have a tight formation, if we have a low viscosity oil, that we will not be able to take a bottom hole sample. It will not enter the vessel. Also, if we need a small volumes, typically in the PVT analysis, we need small volumes. But if we are going to apply an EOR study, for example, we need the larger volumes. So the bottom hole sampling will not be applicable. Also, a more accurate method that we are using bottom hole sampling is to keep the sample as a single phase. So the sample is taken from the bottom of the well and kept as a single phase above the saturation pressure by pressurizing the vessel or the chamber that have the sample while tripping out of the hole. Regarding surface sampling, we can use as a separator or the test package at the wellhead. We can take sample from the separator itself. We can take sample and send it to lab, but at one condition, that the wellhead pressure should be above the saturation pressure or the bubble point pressure or the dew point pressure, which is not the case at the most cases. So what is the solution? The most common surface sampling technique is a separator recombination. So we take a simultaneous sample of the separator oil and the gas, but we should have accurate measurement of the production, and after that we send it to the lab. So we need to stabilize the production, see the trend of gas oil ratio for a few hours, even few days, stable. Then we take a sample from the oil and the gas, and should be at the early stage of production. It shouldn't be from a reservoir that to produce, for example, 1 million barrels, because it will not be representative, because the pressure may be dropped at the reservoir itself below the bubble point. So we have a higher gas production compared that we are having. So it should be at the early stage of production, stabilize the production for a longer time. Then we take an oil sample and gas sample, send it to the lab, and the lab will recombine them. It's recommended to be a backup for a good quality bottom hole sample, but could be primary in case of we need a large volume that maybe we need an EOR study, or the bottom hole flowing conditions is less than the saturation pressure. So we have the bottom hole already is less than saturation pressure, or also we have a high water cut such the fluid may not be representative. Like I mentioned, the main challenge of the recombination is the accuracy of the separator flow measurements and stability of the separation conditions before and during sampling. It should be stable, and we have a clear trend of the gas oil ratio especially, and the water cut. Generally, like mentioned, bottom hole sampling is preferred. However, if we use surface sampling, we should have a valid value of gas oil ratio measured over a longer period of time. So also we have recommendation. We try to obtain the fluid sample before any significant production at the early stage of production, like I mentioned, and bring the well at the lowest possible rate period to sampling and stabilize it. If the rate of the well changes, the separator production should be stabilized even over days. Like I mentioned, we should have very stable parameters in terms of production in order to take a correct sample that can be recombined in the lab. Now we have a sample and we send it to the lab, and we need to get the PVT properties that we talked about. We talked about that we need to get the composition, we need to get the beta O, oil formation volume factor, oil density, oil viscosity, and so on. And in case of gas, we need to get the Z factor, the amount of the dew point pressure, the amount of gas, and so on. So we have some PVT experiments that is performed in the lab and will help us to calculate or get this information. Before I go to this PVT experiments, any question regarding the sampling process?
No question,
Any
Engineer
questions?
Ahmed.
Okay.
Engineer Ahmed, can you hear me?
So
Hello?
in PVT experiments, we have 5 major procedures in case of oil PVT study: composition, flash vaporization or constant composition, CCE, differential vaporization or differential liberation, separator test, and oil viscosity. In case of gas, we have another experiment which is called CVT, constant volume depletion, and we are going to talk about these experiments. Composition, the fluid itself is go through chromatography, and we get the composition of C1, C2, C3, C4, and so on, up to C30 plus, C36 plus, in some labs C50 plus. And it will help us to identify the type of fluid itself, construct the base envelope that we talked about it in the 5 reservoir fluids. Also, it will help us in case we are going to construct an equation of state. And this is an advanced topic that we may cover. But the equation of state represents the very minor changes of the fluid properties under very small changes of pressure and temperature. And it's very important, very accurate in case of you have a reservoir fluid that change very rapidly, very sharply with the pressure and temperature drop. Like, for example, the gas condensate. In the gas condensate, some cases of volatile oils, you should use the equation of state. Also, in some cases related to the flow assurance of the gas reservoirs, you should use the equation of state. So it's very important to get the composition measurements. For the flash vaporization or the CCE, we have the sample. We put it in here in this vessel, and it's pressurized with mercury at a pressure above the reservoir pressure. Then at steps, we reduce the pressure by removing some of the mercury. And then we reduce it a little bit. Then we have an increase of volume. When we drop below the bubble point, we will see in the screen of the lab device itself some gas formation. And we have furthermore drop, we will have an increase of the gas formation. So we are dropping the pressure through stages by reducing the amount of mercury inside the vessel in order to see the volume change related to reducing the pressure. From this data, we can have this volume. At different pressure values, we have the total volume of the cell. And then they plotted against each other. We have this trend and another trend in here. And the cross line between the two trends, we can identify the bubble point pressure. So the bubble point pressure is identified from the flash vaporization data through the total cell volume obtained by reducing pressure at several stages. After that, we have the differential vaporization, which is a kind of different procedure. Now I know the bubble point pressure from the CCE. So I have the volume of the oil, put it at the bubble point pressure. Then I reduce the pressure at step, so some gas form into the cell by removing some mercury. Then I release this gas, and I take this gas to be analyzed, get the composition of this gas and other factors. Then I have another stage of drop in here. After this stage of drop, also another free amount of gas comes out of solution and the liquid volume reduces. So I release this gas and measure this liquid or oil volume. So here we release the gas for further analysis and to calculate the volume of the liquid after releasing the gas. What we have, the initial data that we have from the differential vaporization, we have the pressure, then we have the gas removed as the CC conditions, then it can be calculated as the standard cubic feet calculations, and we have the oil volume as CC, and then we can calculate the gas gravity per each stage. This is different stages. After that, we can revise calculation the gas in solution itself by, if we summed all of these values, you will have this value and we get it again. If you subtracted in here minus this one, you will get another value. So we'll have the gas in solution initially and the gas on solution at each stage. So we can obtain this shape. So we have the gas in solution here and the gas in solution at pressures below the bubble point. So from the differential vaporization, we can know the RS at the bubble point and below it. Then we perform a laboratory separator test, which is the third type of test. Here we have liquid at bubble point. Then we going through separator pressure and then go to stock tank pressure at different pressures. And then we have the total amount of gas released at the separator pressure and the stock tank pressure. We sum it and we have the RS at the at the bubble point conditions. Also, we have the beta O, which is the reservoir barrel in here, at stock tank barrel in here. This is the reservoir barrel, the amount of the oil moved into separator, and this is the stock tank after releasing the gas. So we get two important information. Starting with the bubble point pressure, we move some oil to the separator pressure, which is higher than the standard conditions, and at the stock tank pressure. So we have the amount of reservoir fluid at the bubble point and the stock tank barrel. If we divided the both of them, we will have the beta O at the bubble point. And we have the gas released as separator condition and the gas released from the stock tank condition. Some of them divided by the stock tank barrel, we will have the gas in solution as this. This will be important in two things. First, the correction of the PVT data, like we are going to illustrate in the next slide, and the other one into sizing the separator and knowing the best separation conditions. So if we checked separator test, we will have in here, for example, here we have the set of the separator at 100 psig and the stock tank at 0. So we'll have a gas oil ratio 667 and 92. This is at stock tank conditions. Gas oil ratio at stock tank conditions. This is at reservoir condition. We will take this one, standard cubic feet, stock tank barrel. If you sum of them, we will have the RSP. Also, the stock oil gas gravity will be here, and the formation volume factor will be calculated, like we mentioned, from this volume divided by this volume. And we will have other important parameters, like, for example, the oil phase density and the specific gravity of the flashed gas at the separator conditions and at stock tank conditions. If we perform this experiment at different reservoir, at different separator pressures. For example, we have a bubble point pressure. We can adjust the separator pressure to be 50 psi, 100 psi, 200 psi, 300 psi. And it's very important to have this. Why? Because it will give us the optimum pressure conditions at which that you can the best separation conditions. Because if you check this figure represents separator pressure at the x-axis, stock tank API at the y-axis here, and the solution gas or ratio as this axis. At specific pressure, separator pressure, and it may be different from one fluid to another, you should have an optimum separation. So in this case, at the 100 psi, you have the lowest beta O and the lowest RS and the highest EBI, which is the optimum in this case. And why it's very optimum in this case? Because you released most of the gases at this condition. In some conditions, this figure can be reversed or this figure can be shifted. It depends on the fluid itself. And it gives you some information about what is the optimum separator conditions that shall be used in this case. Another experiment which I talked about, which is called CFD, or constant volume depletion, and it's applied only to retrograde gas condensate and wet gas, which we have gas at a pressure higher than the reservoir pressure. Then we have a pressure drop through removing some of the mercury. Then we have a pressure drop by removing some of the mercury. And then we will find an oil or condensate droplet throughout the reservoir, meaning that we dropped below the dew point pressure. And we, if continue dropping, the amount of the liquid will be increased. This is very important, or it's a replacement for the CCE experiment or flash vaporization experiment, because in case you have gas, we will apply this experiment in order to get the properties of the gas itself. Also, the constant volume depletion, it's more similar to the differential liberation, and it's applied the gas. You can start at the dew point pressure, and if you have a pressure drop, you will have liquid, then you release some gas. But here, it's vice versa of the differential liberation. You keep the volume constant. You don't release all the gas. You remain the volume constant. In the differential liberation, if you remember, we remove all the gases. Here no, we keep the volume constant. So we remove the additional gas only. So we remove some gas in order to keep the volume same. So it's called constant volume depletion, and it's a replacement for differential liberation in case of retrograde gas and wet gas. What we can get from the constant volume depletion, the cumulative gas oil ratio as a function of pressure, also the liquid dropout curve, or the amount of retrograde condensate formed with the pressure depletion, and the relative composition of the gas liquid phases at each pressure stage. The last thing that I want to talk about it, which is the correction of the PVT. So we have this data that we obtained, which is most likely relative volumes, amount of gases calculated, but we need to calculate the important factors that we are going to use, beta O or S coefficient. But we need to correct these values. But why? Because above the bubble point, the data, like we mentioned, is related to reservoir volumes by the bubble point volume. For example, in here, if you checked this relative volume, you will get from this table, if you checked a real CCE data, you will check that it's calculated reference to the pressure of 2620. So we will have a function here called relative volume, and is calculated to this depth. So the volume will be divided in this. So it's reservoir volume by the bubble point volume. But I need the definition of beta O is the reservoir volume to the standard cubic feet volume. So we should correct these values. Also, the below the bubble point volume will have same reservoir volume by the residual volume, and also the gas in solution by the residual volume. However, I want the reservoir volume in case of beta O divided by the stock tank volume, and the gas in solution divided by stock tank volume. So how we can correct it? At the pressures above the bubble point, we need to combine the data from flash vaporization or CCE with the separator test. If we are below the bubble point or below the dew point, we need to get the data from differential vaporization and or differential liberation and separator test. How we will calculate them? If we take the equations, this is very simple equations. At the pressures above the bubble point, we will take from beta O will be calculated from here from the separator test, and then we will have it from the flash vaporization. And the RS will be the RS as same from the separator test. So these two values from the separator test and this value will come from flash vaporization. And this is how we transfer the equations. So we will get the reservoir barrel at the defined pressure as stock tank barrel. We calculate this reservoir pressure at the bubble point as stock tank by reservoir barrel at the pressure and reservoir barrel at the bubble point. So this will go with this, and we will come to the definition of the beta O, and this is for the pressures above the bubble point. For the pressures below the bubble point, we will have this values. Beta OP is the value from separator test, and this is the relative oil volume from differential liberation as the selective pressure that we are going to talk to calculate, and this value also from differential liberation, but at the bubble point pressure from the differential liberation. Similarly, we will calculate the RS from this is the RSP from the separator test, and this is at the selective pressure or the pressure that we want to calculate the RS at it, and here at from the differential liberation also, but at the bubble point pressure. New PVT reports, all these values are currently calculated. So no need to calculate it. It's just adjust it and give it to you. But in case you have an old PVT reports, you need to make this adjustment prior to the use of PVT in order to get an accurate values of beta O and RS. Also, we should calculate the compressibility. It should be calculated, and also the density. If you have above the bubble point, you can use it from the density from the separator test divided by the value from the flash test at a certain pressure. And that's it. This is the end of my presentation. If you have any questions. Someone is asking about the attendance, if anyone from OPA can answer. Any questions? Okay. If you have any questions related to PVT, the application of PVT, any further questions that are not covered in the topic, you can ask me. CCA test is very important not to understand the reservoir, to obtain the bubble point pressure. And of course, we will take these values and use it to calculate the beta O correction factors for other tests above the bubble point. So the CCA test is the main test that we can get either the bubble point pressure or the dew point pressure in case of gas. It's CCE, you can use CCE or it's called flash vaporization. It's the same test. So it's used for both of them. Any other questions? Is in softwares, what is meaning bubble point by matching? Yes, in case of you are going to perform an equation of state, you will enter your composition, perform several processes called lumping, delumping, and so on, and then you will match into the actual experiments that you have. So the matching bubble point that you get, it's by regression the parameters related to critical pressure, critical temperatures of the pseudo components that you have. So you will get a kind of different or similar, should be very near to the original phase behavior. And also you will have some pressure related, calculated from this process. So you will get a bubble point match pressure should be very near in case of formation of equation of state to the actual measured bubble point in the PVT report. Someone is asking if you can open the mic.
If we have a question, please can we sorry, after the session, okay? Thank you. You can continue, Engineer Ahmed.
I
Engineer
don't
Ahmed,
know if you
hello?
can you hear me, Yusuf?
Yes.
Okay. So if I understand your question, you are going to perform an equation of state on software. So you are asking about what is the bubble point pressure by matching.
Okay, but when I dealt with softwares like PipeSim, for example,
Okay.
which is SLB software.
Yes, I know.
So when I dealt with it, I entered I found the bubble point entered by default. So I asked the instructor how what is the logic behind this. He told me that inside PipeSim it used like correlation to found like entry bubble point.
Yes.
Okay, I found the correlation and I made it in my software. I programmed one, by the way, but I don't understand how I can perform the matching after this. What is the type of data that I will add to the software to perform the matching process?
If you work it on the PipeSim in the PVT section, you will see a tab is called the calibration. It will be third cap in the PVT model. Open the calibration and you will see it will ask you to give a point of pressure above the bubble point, a point of pressure at the bubble point, and the point of pressure below the bubble point. And we'll have to enter the RS and the pressure and the temperature. If you enter this value, it will be calibrated to the correlation that PipeSim is using. It will be calibrated to the values you entered. In other softwares, like for example Prosper, which is similar, you can enter your PVT table, perform a regression, and see what is the fit correlation that can be used. Or you can use the table itself. I hope that I answered your question.
Engineer Ahmed, can you hear me, please?
Yes, I hear you.
Okay, thank you.
Okay. Yeah, it's data handling. Yes, you can optimize it in the pipes. Go to the tab calibration in the PVT model. The question from Muhammad Amin: how does PVT behavior affecting enhanced oil recovery? It's very important. It's very important. The PVT in the enhanced oil recovery. For example, if you have a heavy oil or viscous oil, like I mentioned, I worked in very heavy oil field, API 11, viscosity 4000 centistoke. You should use thermal EOR. And the relation between the viscosity temperature is very critical in this case, because the higher the temperature, the good recovery. Also, the steam itself and the reaction between the steam and the fluid composition itself is important, because in some cases you can formulate flow assurance issue like, for example, asphaltene precipitation. This is an example. Another example, if you are performing polymer flooding, the relation between the viscosity of the oil and the viscosity of the polymer solution is critical in the displacement, because you need to achieve a good mobility ratio and to avoid any viscous fingering or early breakthrough related to the viscosity difference between the injected fluid and the oil produced. So the relationship between the water and or the polymer and the reservoir fluid is critical to be understood before starting the process, as you may have unfavorable mobility ratio that could cause early breakthrough affecting the product commerciality. Also, for example, if you are using surfactant or other chemicals, it's related to composition to select the best type of surfactant that will reduce the residual oil used. All of this I can recommend to you. There are SPE comparative cases, small sector models performed on Eclipse different models that show the effect of the changing of viscosity, changing of the injection fluid parameters, changing of steam. I think it has a case of steam injection, and you can see the effect of changing these parameters on the recovery factor of this sector model. You can see clearly what is the effect of the PVT on the recovery. Any questions? Last call, any questions?
There is no question, Engineer Ahmed.
Okay, thank you very much.
Thank you, Engineer Ahmed. Did we finish?
Yes, I'm done.
Okay. Thank you for a great question, and thank you all for attending this session. If anyone have a question, please write in the chat box. Okay, thank you all. Thank you, Engineer Ahmed. Thank you.
Thank you.
Bye-bye.